Okay, here are your notes for section 9-2, and today we're going to talk about exponential decay. I have a journal choice for you, and what you're going to do is you're going to compare and contrast growth and decay curves. Okay, it's a pretty easy comparison, especially after you look at the graphs and these types of word problems that we're talking about, so I think it would be an easy one for you to do. Let's talk about what you think exponential decay could be. We just talked about exponential growth, so you should have a good idea now at this point what the curve looks like and what's happening. Something is getting large exponentially. You're multiplying by something over and over and over to get something larger. So what we're dealing with when we talk about exponential decay is when that growth factor that causes the exponential growth to get bigger is between 0 and 1, and we kind of talked about this yesterday, it's going to get smaller, okay? So instead of exponential growth, it's going to be something that's exponentially getting smaller, so instead of something looking like this, we're going to be dealing with something that looks more like this today. Depreciation as an example. Automobiles and other manufactured goods that are used over a number of years often decrease in value a lot. They always say, and I'm sure Mrs. Wolfel would know more about this than I do, how a new car is a really horrible investment because it depreciates so much unless you just like it for your own enjoyment. It's not going to keep its value. The function that maps the year onto the value of the car is an example of an exponential decay function. So those values that they get out of that Kelley Blue Book or whatever, I think that's what it's called, those trade-in manuals, they use a math formula and it is a model off of exponential decay. Let's talk about decay of this new piano. A new piano costs $8,500 and it depreciates 6% each year. Write an equation that gives the piano's value when it is T years old. Okay, so that formula that we were dealing with for exponential growth is the exact same. It's going to be y equals a times b to the x. A is going to be our initial condition. B is going to be that growth factor. Okay, so we're going to have y equals, that initial condition is $8,500. The growth factor here is what is tricky. You are going to be very, very, very tempted to put 0.06 in there. I want you to think about what that means. If I have a piano that's $8,500, if I take 8,500 times 0.06, you're telling me that the value after 1 year has dropped all the way to $510. That makes no sense. The piano does not keep, the growth factor is not 0.06, it's actually 0.94, okay? It's keeping 94% of its value. So you need to take 100, or 1, minus the percent 6, or you could have done 1 minus 0.06 and get 0.94. The growth factor has to be less than 1, yes, but it won't be a ton less than 1 unless it's dropping significantly. Okay, and then we're going to put T in for time. So what is the piano's value when it is 5 years old? Y is 8,500 times 0.94 to the 5th power. Take 0.94 to the 5th power first in your calculator. Keep that in there and multiply it times 8,500. And it looks like $6,000, 6238.18. Okay, this is going to be the tricky part of the lesson. If you're going to make a mistake, this is where it's going to be. That growth factor. 94% is nowhere written in the problem. You have to come up with it based off that 6%. But you can do it. Okay, let's look at something else. This is, I say fun fact, you're going to say this isn't fun at all. But basically what you are going to talk about, what I'd like you to realize is the relationship between exponential growth and exponential decay and linear growth and linear decay. Do you remember when we talked about that? Linear increase and linear decrease. You had your initial condition, which happened right here. And then we graph it. This is linear growth, initial condition, positive, so it was growth, okay? Linear decay, initial condition, decreasing, there it is. 0 is the pivot point in linear increase or decrease. So if I have y equals we'll put kx plus b instead of mx plus b. If I have numbers bigger than 0, it's going to be increase. If it's less than 0, it's going to be a decrease. When you have exponential growth or decay, you still have your initial condition, which happens to kind of be like a y-intercept here. But what determines if you have a exponential growth or exponential decay is not the breaking point of 0, positive and negative. It's greater than 1 or less than 1. You're not going to have anything negative. It's all going to be positive. But if you have a number bigger than 1, you can have growth. And if you have a fraction, something less than 1, bigger than 0, it's going to be decay. So they are related. Let's talk about half-life and radioactive decay. In lesson 9.1, you saw that when a quantity grows exponentially, it's doubling. Time is constant. If a substance decays exponentially, the amount of time it takes for half the atoms, you've heard about this before, to decay is called half-life. Half-life is an important feature of some chemical processes. Okay, I don't really want to go into all this because it's not very interesting to me, although some of you will find it fascinating. What half-life does is we're still going to use the y equals ab to the x form. Still your initial condition. What b is going to be, what's that growth factor? We're talking about half-life, so b is going to be 1/2 or 0.5. This is what's going to be tricky. This is not time in years. This is time in half-lives. So it'll tell you how many, you have to figure out how many half-lives to plug in, half-lives I guess, how many half-lives to plug in. So if it's saying, if it was 3 years, you're not necessarily going to plug in 3 if that's not what the half-life is. Kids do have a little bit of a hard time with some of these problems, so make sure that you pay attention to this. I'm going to write not years. I'm going to put an exclamation point. Okay. Let's look at this example. I don't know what that's called. Strontium, I think, maybe. Has a half-life of 29 years. This means that in each 29 period, that's when half of them go away. So in order for us to use that growth factor of 50% or 1/2, I need to relate my time to that. So how many grams of 90 whatever remain after 6 half-life periods? Okay, so this I'm going to actually plug in for x. My formula is going to be y equals 1,000, that's the initial condition, times 1/2 or 0.5 to the x. 6 half-lives. I'm plugging half-lives in, so this is good. 0.5 to the 6, and take that times 1,000. And I get 15.625. How many years is 6 life periods going to be? Well, that's 6 times 29. 174 years. I should have wrote that here. Okay, so while this asks how many grams are in 6 half-life periods, that's one thing. What if I asked how many grams were in 100 years? Well, you need to figure out how many half-lives that is. So when you plug into x, you would plug in 100 divided by 29, because that will tell you how many half-lives, and it's like 3.44, but you could just plug in that fraction in for x, and you could tell how much of that chemical would be left. Is it a chemical or atom or whatever it is? A gram? I don't know. Okay, does that make sense? Because this is what kids struggle with, this part right here. We're going to write a recursive formula for a sub n, the number of grams that remain after n half-lives. Some of you still struggle with recursive formulas a little bit. What is the initial condition? We write a sub 1 equals, well, it was 1,000. After that, what do? The mystery term is the term before it times 1/2, or you could put 1/2 a sub n minus 1. How do you finish these up? We have to say for integers n greater than or equal to 2. Okay, and when I just looked at the book here, they're not always using a sub 1, they are using a sub 0 sometime, which is okay also, because that was the notation they use a lot of times for exponential growth and decay. For initial is a sub 0. If that's the case, The mystery term would be 1/2. The term before it, so it's still n minus 1. This is the same. What's going to change is your 4 integer statement. N greater than or equal to what? Well, this worked for 0. What's the next one I need? 1. Either one of those would be acceptable. The reason they wrote it this way in the book instead of this way is because they want you to write the explicit formula. And we already did that whenever we were actually figuring it out. A sub n is your initial condition, 1,000, times 1/2 to the n. By writing it this way instead of this way, we are allowed to use the n instead of what we're supposed to use on the geometric sequences, the n minus 1. Okay, so now write a formula for the amount of 90 SR remaining after any real number of half-life periods. Well, that was the same thing. Actually, I did that for part A. The initial condition, 1,000 times 1/2 to the n, or x. It says half-life period x, so it's x. Okay, I guess you could have figured this out just by repeated multiplication, and that's kind of what they anticipated you doing, and we went straight to the formula. Either way will be fine. You could do repeated multiplying. After 6 half-life periods, you could take 1,000 times 0.5 times 0.5 times 0.5 6 times, or you can do the formula. I encourage you to use the formula. It's going to be more accurate for you. Okay, let's do another one. Where's the shape thing? Okay. Suppose a sample begins with 80% pure carbon-14. Use the information in example 2 on page 588 and 589. Pull that up here. Carbon-14, here we go. Carbon-14, sometimes written like this, has a half-life of 5730 years. Suppose that an object contains 100 grams of carbon-14. Let A sub n be the number of grams of carbon-14 after n half-lives. So they want to use the this is tricky. Okay, they want us to use this half-life. That's the reason they referred us back to this. What is happening in this example is because it says 80% pure carbon. We don't know how many grams. So our initial condition that we are going to use is this 80% notation. We're going to say 0.8 is our initial condition, because we're going to be talking in terms of percentages here. So the initial condition is 0.8, and the half-life, so we're doing times 0.5 to the n, and the n is going to, I'm using n instead of x because that's number of half-lives. So this is going to be our formula. And I do think that was a little confusing because it didn't tell you the initial condition outright in grams, so that's where we're using that 80% from. Then what they want us to do is graph your equation in part A and use it to find the age to the nearest century of the sample containing 60% of the original half-life. So what they're looking for is y to be 0.6. They want 0.6 to equal 0.8. 0.8 times 0.5 to the x. So what we're going to do, if you remember, is we're going to graph y equals 0.8 times 0.5 to the x, and we are looking for when does it equal 0.6. I already have my calculator here. 0.8 times 0.5 to the x. Okay, enter. I need to look at the table. Okay, and I'm looking for how many half-lives until it's 60%. Well, it's going to be between 0 and 1. It's going to say how many, used to find the age to the nearest century. Okay, 60%. So between 0 and 1, so I'm going to change my table settings. Let's go by 0.1s. 60% looks like between 0.4 and 0.5. Let's go a little bit closer. Start at 0.4. Now we're going to go by 0.01s. And that's pretty close. Let's say 0.4. Let's say 0.41. Okay? So we get x equals 0.41. That's 0.41 half-lives. We go back to the textbook to see how many years are in the half-life, and it says 57 30-year period. So 0.41 times 5,730 will tell you how many years. And it looks like about 2,350 years. Okay, and I will tell you that I just looked that up, and the textbook actually went to 0.001. They used 0.415, and then they got a little bit closer. It's 2,400, but I put dollars. That's years. The year 2,400. Okay? Alright, I hope that makes sense, this half-life stuff. Next thing we're going to talk about is the definition. If a positive quantity A is multiplied by B and B is greater than 0, then after a period of length x, the amount of the climb AB to the x. Okay, basically you just really need to know what this formula is and realize that B is telling you what type of graph we're looking at. If it's here, we're talking about decay. If it's bigger than 1, we're talking about growth. We're going to look at the graphs, try to come up with some things on domain and range by looking at the activity on page 590. Okay, and what they want us to do they want to graph different f of x values for b to be between 1 and 4. So let's do, did I tell you what a is? For a constant value of a greater than 0. So we got to pick something. Let's pick 2. Would you like 2? So we're going to do 2. Where's my graph? There it is. Menu, table, actions. How do you hide the table? You guys are all telling me to the screen and I can't hear you. I think it's like Control T. But that doesn't let me do that. There it is. Okay. So let's look at some of these. We're going to use 2 for A, and they want us to try different values of 1. So 2 times, let's do 1 to the x, enter, looks like a line, okay, tab, 2 times 2 to the x, 2 times 3 to the x, and 2 times 4 to the x. So what is changing? What is staying the same? Okay, what's changing is the steepness of the graph, okay? What did I change? I changed that b value. And so what this tells me, when I go back to my notes here, is that b changes the steepness. And that's for exponential growth. But that y-intercept remained constant. That y-intercept is going to be that a value. Now if I pick values of b between 0 and 1, what's going to happen? I'm going to guess that it's the same thing. So instead of 1, 2, 3, 4, now we're going to pick 1, and let's do 0.5. I did 0.4, I guess, so we'll do that. 0.4. 0.3. Let's do 0.2. Okay, so what do we have here? Let's see. 0.2 is in purple. 0.3 is in blue, and 0.4 is in green. So I'm guessing if I pick 0.5 or 0.6, it's going to get a little flatter even. The y-intercept still was that a value. What about the x-intercept? Is there an x-intercept on those graphs? We talked about that already. None. There is a asymptote on the x-axis. So that's y equals 0. So let's talk about the range. The range always is going to be, for both of them, we are looking at numbers y greater than 0. Never equal to 0 because it cannot touch it. And the last thing is as x increases, y is going to decrease on decay, and it's going to increase on growth. Basically, it is important to kind of play around with these different graphs to see what you're dealing with, what numbers change what. The big one that's going to help you a lot, though, is that y-intercept point being a. That's really going to help you graph a lot. Okay, that's all I have for today. There is some homework problems for you, and I will talk to you about any questions you have tomorrow. Thank you.